Space is enormous, counterintuitive, and full of facts that sound impossible until we break them down. Today we'll walk through 11 striking space facts, explain the physics behind each one, give the important caveats, and offer simple viewer actions or calculators you can use to explore the ideas further. Let's begin. Fact 1. If you shout in space, nobody hears you. Sound needs a medium, air, water, or solid material, to propagate. In the vacuum between planets and stars, there are essentially no molecules to carry pressure waves, so a shout does not travel. That doesn't mean silence can't be recorded where gas exists, or that electromagnetic signals aren't used for communication. Radio waves travel through vacuum easily. Caveat: inside a spacecraft or on a planet with an atmosphere, sound behaves normally. Practical idea: demonstrate this concept visually by showing a side-by-side, a person shouting inside a pressurized cabin with waveform, and the same shout shown as no waveform in a vacuum simulation. Let's move on to fact 2. A day on Venus is longer than a Venusian year. This sounds impossible, but it's a result of the planet's bizarre rotation. Venus spins on its axis incredibly slowly, and it does so in retrograde, that is, backwards compared to its orbit around the Sun, and the rotation of most other planets in our solar system, including Earth. One full rotation, which is its sidereal day, takes about 243 Earth days. In contrast, it completes a full orbit around the Sun in just 225 Earth days. So, its day, measured by its spin, is longer than its year. Because of this backward rotation, the time from one sunrise to the next, its solar day, is much shorter, about 117 Earth days. Now for fact 3, black holes aren't perfectly black. In the realm of quantum mechanics, they actually glow. This phenomenon is known as Hawking radiation. In 1974, Stephen Hawking theorized that quantum effects at the edge of a black hole's event horizon would cause it to emit thermal radiation, almost as if it were a warm object with a specific temperature. This happens because of virtual particle-antiparticle pairs constantly popping into and out of existence in the vacuum of space. When this occurs right at the event horizon, it's possible for one particle to fall into the black hole while the other escapes, carrying away a tiny amount of energy. To an outside observer, it looks like the black hole itself is emitting particles. However, you'll never actually see this glow. For astrophysical black holes, the temperature of this radiation is incredibly low, far colder than the cosmic microwave background radiation that fills space. The energy from a black hole's accretion disk, the swirling matter falling into it, completely overwhelms this faint quantum signal. While Hawking radiation remains a theoretical concept that is too weak to be detected from actual black holes, its importance is monumental. It represents the first major breakthrough in uniting Einstein's theory of gravity with quantum mechanics and thermodynamics, suggesting that black holes not only have a temperature, but also eventually evaporate over immense timescales. Fact 4. Astronauts can become roughly a few centimeters taller in microgravity. On Earth, gravity constantly compresses our spine, but in the free-fall environment of space, this pressure is lifted. The fluid-filled intervertebral discs, which act as cushions between our vertebrae, are free to expand and absorb more fluid. This causes the spinal column to lengthen, making an astronaut temporarily taller. The effect is not permanent. Upon returning to Earth, gravity quickly gets to work, and the discs recompress over a few days or weeks. Measured mean increases are in the order of 2 to 5 centimeters, which can be up to a 3% increase in spinal length, depending on the individual and the duration of their mission. However, this temporary height boost comes with significant physiological costs. Without the constant load of gravity, the body begins to decondition. Astronauts experience atrophy in their muscles and a decrease in bone density, which are serious health concerns. To combat these effects, astronauts follow rigorous daily exercise regimes, often for 2 hours a day. These countermeasures, including treadmill running and advanced resistance devices, are crucial for maintaining muscle mass and bone strength, ensuring they can safely return to Earth's gravity. Fact 5. The Sun contains about 99.86% of the total mass of the solar system. This single star is so dominant that everything else, all the planets, moons, asteroids, and comets combined, makes up a mere 0.14% of the system's mass. This immense concentration of hydrogen and helium is the gravitational anchor that holds our entire solar system together, dictating the orbits of every object within its influence. Even planets that are enormous in volume are just gravitational footnotes by comparison. Within that tiny remaining fraction of mass, Jupiter alone is a giant. It is more than twice as massive as all the other planets combined. Yet, even this king of planets is minuscule compared to the Sun, containing less than 0.1% of the solar system's total mass. A scaled mass pie chart powerfully illustrates this. The Sun's slice is nearly the entire circle. Only by zooming into the sliver representing the rest of the system can we begin to appreciate Jupiter's contribution relative to its planetary neighbors. Fact 6. The Andromeda Galaxy is approaching the Milky Way at a staggering speed. The component of its velocity directly towards us, its radial velocity, is estimated to be around 110 kilometers per second. That's fast enough to travel from New York to Los Angeles in about 36 seconds. This cosmic approach is driven by the mutual gravitational attraction between the two largest galaxies in our local group. Billions of years from now, this gravitational dance will culminate in a slow, majestic merger. It's important to note that this 110 km/s figure is only the part of the motion aimed at us. Andromeda also has a significant sideways, or transverse, velocity. The interplay of these movements within the complex dynamics of our local group will determine the exact collision timeline. Despite the term collision, individual stars are so far apart that direct star-on-star impacts will be exceptionally rare. Instead, the two galaxies will pass through each other, their structures distorted by gravity over hundreds of millions of years, eventually settling into a single, larger elliptical galaxy. Fact 7. A spoonful of neutron star material would weigh an astronomical amount here on Earth. These incredible objects are the collapsed cores of massive supergiant stars, packing more mass than our Sun into a sphere just a few kilometers across. Estimates depend on the chosen volume and local assumptions, but a single teaspoon of typical neutron star matter is on the order of 10^12 to 10^13 kilograms. That's commonly quoted as a few trillion kilograms or a few billion tons, equivalent to the weight of a mountain. This enormous density arises because the star's gravity is so immense that it crushes atoms, forcing electrons and protons to combine into a super-dense sea of neutrons. Matter is compressed beyond its atomic structure into pure nuclear densities. Caveat: it's crucial to understand that neutron star matter cannot exist stably under Earth's conditions. If you could magically teleport that teaspoon here, it would decompress instantly and violently, producing catastrophic effects with the energy of a massive bomb. The pressure keeping it stable is gone. For a practical explanation, let's compare densities. Ordinary water is about 1,000 kilograms per cubic meter. Neutron star densities, however, are an almost incomprehensible 10^17 to 10^18 kilograms per cubic meter. It's a state of matter so extreme it defies our everyday intuition and can only exist under the crushing gravity of its stellar remnant. Fact 8. Space is effectively silent. This is because mechanical sound waves, which are vibrations traveling through a medium like air or water, do not propagate through a vacuum. There are simply not enough particles for the vibrations to travel between. That's different from saying electromagnetic signals like radio waves or particle streams from the Sun don't travel. They do, as they don't require a medium. Inside the gases of a nebula, the plasmas of a star, or within planetary atmospheres, you can absolutely have sound. But in the vast, near vacuum of interplanetary and interstellar space, the classic Hollywood whoosh of a passing spaceship is pure fiction. Caveat: while you can't hear in space in the traditional sense, radio astronomy and the study of plasma waves provide other kinds of sounds. Scientists can capture these non-auditory signals with instruments, and then convert them into the audio range for us to hear. This process, called data sonification, is a powerful tool. It allows us to hear the crackle of Jupiter's magnetosphere, the whistle of plasma waves, or the rhythmic pulse of a distant pulsar. We can illustrate how we hear space via these instruments, turning silent data into meaningful soundscapes that reveal the universe's hidden dynamics. Fact 9. Jupiter is so mind-bogglingly large that by volume, it could contain all the other planets of our solar system combined, with room to spare. Jupiter's volume is roughly 1/300 times that of Earth's. When you take the time to sum the individual volumes of Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, you find that this entire collection of worlds can still be enclosed comfortably within the colossal sphere of Jupiter. It's a testament to the sheer scale of the gas giant, which truly dominates the planetary landscape of our solar system. Caveat: however, it's important to remember that volume isn't the same as mass. While Jupiter wins on size, it's Saturn and Jupiter together that truly dominate the planetary mass of the solar system, accounting for over 90% of it. But even their combined might is trivial compared to our star. The Sun contains 99.86% of all the mass in the solar system. Jupiter, for all its grandeur, is less than 1,000th the mass of the Sun. A practical graphic stacking planet volumes into a Jupiter-shaped container shows its size, but a mass comparison reveals the Sun's ultimate gravitational authority. Fact 10. Estimates of the number of galaxies in the observable universe have changed with deeper surveys. Older estimates suggested hundreds of billions. Newer deep-field observations revise these numbers and reveal previously unseen faint galaxies. Saying 100 billion new galaxies discovered each year is a dramatic simplification. What's accurate is that modern surveys and instruments detect millions of new galaxies, as telescopes probe fainter magnitudes, and revisions to total counts arise as we expand survey depth. Caveat: galaxy count estimates are model-dependent and change with instrument sensitivity. Practical tip: show Hubble and JWST deep field images, explain selection effects, and emphasize the difference between galaxies detected per survey and total galaxies in the observable universe. Fact 11. Time dilation in relativity means travelers moving at high speed or deep in gravity wells experience time differently. They age slightly less than people remaining farther from mass or slower. In practice, astronauts on the International Space Station age microseconds to milliseconds less because of their speed and weaker gravitational potential relative to Earth's surface. GPS satellites require built-in relativistic corrections to keep clocks synchronized. Caveat: the aging effects are tiny for current human missions but become large at relativistic speeds. Practical demonstration: show a simple relativistic time dilation calculator and compare the astronaut example to hypothetical high-speed travel. Across all these facts, a consistent storytelling approach improves credibility. State the claim, explain the mechanism briefly, give the numerical context and caveats, and show a simple visual analogy or safe activity for viewers. Examples of accessible viewer activities: run a relativity calculator with inputs for ISS speed, compare a planetary rotation versus orbit simulation for Venus, or explore published deep field images to see how fainter galaxies appear with longer exposures. Finally, pick one idea from the video. Try the relativity calculator, time a high-speed octopus clip, or compare the Sun's mass fraction in a pie chart, and tell us what you learned in the comments. Subscribe for more clear, practical space science and careful explanations that put headlines into context.